This is Software Engineering Radio, the podcast for professional developers, on the web at SE-Radio.net. SE-Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE-Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
For Software Engineering Radio, this is Robert Blumen. Today I'm joined by Monica Beckwith. Monica is an independent consultant specializing in optimizing the Java virtual machine and garbage collection for enterprise applications. She's a regular speaker at conferences and has published articles on topics including garbage collection, the Java memory model, and others. Monica was the performance lead on the G1 garbage collector and named a Java 1 2013 Rockstar. Monica, welcome to Software Engineering Radio.
Thank you.
Is there anything else about yourself you'd like the listeners to know?
No, I think that you summed it up pretty well. I've been working as a performance engineer, Java performance engineer, for more than a decade. I used to work for Advanced Micro Devices, and that's how I kind of got into the JVM, GC, JIT compiler realm. And I worked primarily with Hotspot, which is like the OpenJDK Hotspot garbage collector, and the compiler, the JVM itself. But I've also briefly worked with JRocket and IBM's J9. So yeah, it goes along. I started with just optimizing using the right instructions, optimizing the generated code. Eventually moved on to trying to optimize the compiler, the JIT compiler itself, and then finally moved on to garbage collector, and then that's where I stayed. I kind of worked with the garbage collector, mostly server-side garbage collection. So like the throughput collector, worked with CMS, mostly concurrent mark and sweep, and then finally G1 GC, and that's where I've been working with G1 GC for a while now.
I'm really looking forward to your insights on garbage collection, which is the topic of our show. I'd like to start out with some basic background, starting with the question, what is garbage?
Garbage in simple terms is something that you don't need anymore, that is not referenced anymore. When you look at for example, in Java, when you look at the Java heap, objects are allocated on the heap. Most often than not, you can think of it as sort of a linked list. So you have the root set, and then whatever is referenced from the root set is live, right? And then you need to mark it and so on and so forth. But what is not referenced is still occupying space in the heap. So that needs to be collected, so to speak, or sweeped, So that the unreferenced object, which is not referenced by anything on your heap, any other object on the heap, and doesn't directly connect to the root, indirectly or directly connect to the root set, then that can be reclaimed, and that is known as garbage. Okay.
Could you describe a basic garbage collection algorithm that would be common to any language that has garbage collection?
Sure. So garbage collection, let's start from what garbage collection means. It's not just the collection itself, but it's also the allocation. So, for example, in Java, when your application allocates an object, it gets the garbage collector handles the allocation, and then there is the fast path allocation, usually, which is optimized to not have synchronization overhead. Then there comes the collection part, where when the objects are not reachable, they need to be swept, they need to be collected. So what happens is that the heap is a finite amount of memory, and so if you talk about generational heap, for example, when the young generation or the old generation gets full, and you cannot allocate anymore or cannot promote anymore, that's when the garbage collector kicks in. For the garbage collector to start at a particular point and kind of make an object graph, the object tree, those trees need to have one or more root objects, right? So what I mean by these root set, basically like local variables, right? And then your Java threads themselves. If you have the active Java threads, then those are your GC roots. Those form your JC roots. There's also the JNI references, static variables, and such like that. So you start from that set, and any object tree that's reachable from the root set is considered live, and that's what is called as marking. So you're marking all the live objects. So once all the live objects are marked, what's remaining are the ones that are not reachable. When you're doing this object graph, and so those don't seem to fit in the object graph. So those are considered garbage. And then you have different algorithms to take care of that garbage, right? So there's most commonly known as sweeping, and then sweeping is also optimized. You don't have to go through the entire heap to sweep to collect these garbage. You can have, for example, what CMS does has a free list. So as and when it goes through, when it's doing this sweeping, these garbage spaces are maintained in a free list, so you don't have to go through the entire heap. So there are different optimizations that you can do, but most common algorithm you would find that every garbage collector has to mark, and then has to take care of cleaning up, and the way it cleans up could be scavenging and all those things. Are different algorithms that you could go ahead and optimize. And I think the hotspot garbage collector, most common ones are the young generation is a copying compacting collector, and the old generation, the fail-safe one is mark sweep compact. And and then there is the CMS, which is mostly concurrent mark sweep. There's no compaction. There is G1, which does incremental compaction. And
okay.
Yeah.
You talked about hotspot, CMS. These are different garbage collectors in Java. Java has been a garbage collected language since the beginning, but it has changed its approach considerably. Tell us about the history of garbage collection within the Java language, and what sort of goals or what has been driving the changes in garbage collection?
Well, you were right on target. Java always has had automatic memory management, because that takes care of allocating and deallocating. So you don't have to do it like you would have to do in a programming language like C. And that way, the whole purpose was that users don't have to take care of it, because in C we have a lot of problem if you do not deallocate. You keep on using up memory, and you forget to deallocate or whatever happens. But Java takes care of it, and one of the reasons is that it's heap based, right? So we have a finite amount of heap, and which you can set with your maximum. XMS and XMX options, so initial and maximum heap sizes. And so at first it's always been a simple algorithm, like I said, mark, sweep, and compact or whatever. So in Java, in hotspot GC, we started with something called the serial GC. Very simple, single-threaded collection, right? So it pauses the application threads, does its collection just using single garbage collector thread. So that way the data structures are very simple, minimal footprint, and that was working great. And then we figured out that the heaps are growing. The server demands are growing. There are multi-cores that have come in. Java has always been a multi-threaded application, programming language. And so now we wanted to make sure that the garbage collector is growing with the needs of the market, right? So then in comes this throughput collector. But before even the throughput collector, we were hitting a bottleneck with that single generation. So every time that it had to pause, it paused and collected the entire heap. So marked the entire heap, collected the entire heap. that was not working because now you have this humongous pause and only, and then you collect. And so if your heap is growing, so you have to mark and sweep the entire heap, this huge heap. So then in comes this generational collector. So the principle of a generational collector is that most objects die young, which makes perfect sense because a heap doesn't have similarly aged or aging objects. What happens is that when you're allocating, you may be creating more garbage within the first few seconds of your allocation. And then at the same time, you're building up this cache or building up this what we call is live data set while you're also doing other allocations that may not eventually end up in your live data set. So the generation principle is that you allocate these young objects in something called the young generation, and then you age them. And the way you age them is that you move them back and forth in the survivor space. And then once you have aged them appropriately, you promote them into the old generation. So now, hopefully, the goal is that the old generation has what we call a live data set. So your long-lived object, not medium-lived, but long-lived objects get promoted. That's the whole goal of this generational collection.
Right. So what you're talking about generational then is there might be some global objects that I load from a database or config file that I load right at the beginning, and they're going to be there for the entire duration of the program runtime, whereas inside a little function, I need a string, and it gets allocated, and I almost immediately don't need it. So you're trying to optimize different garbage collection strategies based on these very transient objects and more like a permanent object. Is that where you're going?
Yes. So, for example, like you said, something that you allocate like a string and you don't need it, that kind of, if for example, you had put it in the old generation, if for some reason we didn't age it appropriately and immediately promote it into the old generation, now what happens is that when it dies, it creates this hole in the old generation, but it's still there. Even though it's garbage, it's still there, and it's occupying this space that could have been used for your long-lived objects. So eventually, if you have more of these short-lived objects that would have stayed in your old generation is full of garbage, and now you need to kick in an old generation collection. Old generation collections are usually more expensive because old generation usually is a bigger chunk of your heap.
So you want to do the more transient ones more frequently, lower cost, more aggressive collection. If you can sort things into the old generation, they may not change, and you may not have to garbage collect those very often.
That's the goal, especially with something like this concurrent mark and sweep collection. What happens there is that old generation collection is mostly concurrent, and at the same time, it's not compacted. So if you prematurely promote your objects, and then concurrent mark and sweep kicks in, it just sweeps it. So you have in-space deallocation, and then of course you have this free list, which kind of keeps track of all these deallocated spaces. That when the new objects are promoted, they have to fit in these chunks of free space. So sometimes they may not be able to fit in the chunks of free space, and eventually you could run out of old generation space. And unfortunately, even though if you think of it, your entire old generation is not live objects. They're garbage. There's these chunks. But unfortunately, since you cannot fit in your promoted objects in those chunks, you are experiencing fragmentation.
So fragmentation is where you might have enough free memory if you added it all up.
Yes.
But there isn't a single spot that is large enough for the allocation that you need to do.
That is correct. And that's a big problem with concurrent mark and sweep. So to handle that, what happens is the fail-safe, the fallback mark sweep compact GC, which is also called the full GC, kicks in, and then it handles the entire heap, and it's single-threaded. Just like in the serial GC. So it's a long, slow process. So what people end up doing to avoid that, they have at the end of their day, like, they kick in the full GC, and throughout the day, they just deal with young generation collections and sweeping, which is really fast. So there are lots of quirks around it.
Yeah. So you did mention compacting. That is my understanding. It's like when I run disk defrag on my computer, but it's on the working memory in the heap. Is that right?
So compaction is handled different ways in different generations. The way it's handled in young generation, it's done by copying. So if you think of if you draw up this kind of semi-spaces, one is called, let's call the leftmost one Eden, and then we'll call the rightmost one as survivors. Within survivors, you can have S0 and S1, not with G1 GC, but in the predecessors you had S0 and S1, which is survivors.
So G1 is another one of the Java garbage collectors.
Yes, and G1 just has Eden and survivor space. The other garbage collectors have Eden, from space, and to space survivors, or you could call them S0 and S1 survivors. So let's just so when allocations happen into the Eden, after the Eden gets full, there's a young collection is triggered. So when the young collection is triggered, all the live objects are copied to the survivor spaces, and in prior to G1, they copied in, say, S0 from space. So when the next collection happens, which means the next time the Eden gets full, Eden plus S0 are live objects in Eden plus S0 are copied into S1. So this copying back and forth of from S0 to S1 of surviving objects is called copying compaction. That achieves compaction by itself, because after every collection, Eden is completely empty, right?
Okay, so when you copy, you've got from space, you've got little chunks in between the memory in use. So when you copy everything contiguous, correct?
Yes, you copy everything. Yeah, but there's also T labs and promotion labs, and that I'm not talking about here. So that's a whole thing. So when you're promoting, for example, your garbage collection threads will promote into their promotion labs, which is local area buffers. So that way, so there could be some kind of non-contiguous depending on which thread gets to what object first. So there's like a work stealing and all those things that goes around in parallel when parallel threads are employed. It's similar to whatever optimization you would do if you had multiple threads, right? You would have a work queue, would have work stealing.
You talked about these evolution in garbage collection driven by the need for Java to keep up with market demands. One of the most crucial features of modern computing is the large number of cores and memory. I can get an instance on AWS cloud with over 200 gigs of memory.
Yes.
Do the modern Java collectors scale up well across many cores and large memory?
Yeah, that's a good question. So this is one of the reasons why first garbage collector was introduced. So like I mentioned, for CMS and for throughput collector, we have these two generations that are contiguous, young generation and old generation. And as the heap grows, as the number of live objects are increase, because the reason you need more heap is because you're trying to increase your live data set. That's the hope, right? I mean, also, some people increase the heap because they want to avoid a full collection as well, old generation compacting collection as well. So,
did I understand earlier you said you might deliberately run, like as an operational step that a person or a batch job does, the full collection at certain times of day when either you've taken that node offline or it's a load?
Yeah.
Okay.
Yes, and people do that all the time. Yes. So back to so there are lots of reasons why people may want to increase their heap. So let's assume that you have one of the reasons that you're doing it is because you have an increasing amount of live data set that you want to fit in your own generation, and you want to have a collector that is also guaranteeing certain max response time. So a garbage collector that doesn't guarantee, but you want to keep the pause low because right now in hotspot there's nothing that as a hard pause time guarantee, so to speak. But there is a collector called garbage first garbage collector, which is a soft real time guarantee. So it tries to do its best to match your pause time requirement. It doesn't mean that it stops the pause right at your target, but it'll try to adjust its generations and regions so that it can achieve that target. Now, another good point of why people may move to garbage first garbage collector, especially when they have larger heaps, is because of the incremental compaction. I briefly mentioned that it's called mixed GC. So what happens is a G1 heap is divided into regions, and the heap is contiguous and the generations don't have to be contiguous, which means that at a particular time, any region could be a region out of the young generation, or it could be a region out of the old generation. So when we have to, there's a threshold similar to concurrent mark and sweep collector. There's a threshold, marking threshold in G1 as well. Once the old generation gets filled to your threshold, you start the marking cycle. So the marking cycle will go ahead and mark a similar thing, right? So go and mark and find out the live object graph. Now, and it also, there's something called the GC efficiency. It also arranges based on the liveness per region. So if a region is too expensive, it's too popular, so that means remembered sets are expensive, or too many live objects in there, that region will not be collected. It's deemed too expensive. So mostly garbage first, right? Whatever has more garbage will be collected. That's the principle of garbage first. So after the marking completes, there's something called a mixed GC, which has all the young regions and a few candidate regions from the old generation, so old regions. And it does this incrementally. It doesn't collect the entire old generation, but it does so in steps of, maybe you'll see 4 mixed collections or 8 mixed collections after the marking. So that way, if you had a 400 gig heap, like you mentioned, or 300 gig heap, like you mentioned, you're not collecting the entire, say, and your old generation was, say, 200 gigs or whatever, right? You're not collecting the entire 200 gigs at a time. You're collecting it incrementally. So that is a big step for hotspot, because the previous garbage collections may have had, they have a sweet spot, which is definitely way, way less than 200 gigs, right? 100 gigs.
So I wanted to talk about pauses. Well, let's start. You mentioned pauses. Explain what a pause is in garbage collection, and why is there a pause?
Okay, so for hotspot garbage collectors, there's always going to be stop and want pauses, right? And the reason it needs, for hotspot, that it needs to be, is that your application threads have to come to a safe point where they can park themselves, and the garbage collector goes up and cleans, okay, or moves objects around, right? Because like I mentioned about the copying collector, it's moving from one space to the other. So the live objects are moved around. Same goes with compaction. You're moving objects, the live objects. So
right. So you don't want to move memory while the program is running, because you might mess something up pretty badly.
And some in G1 there's concurrent marking, and there's the marking algorithm also has barriers when something writes to it while it's concurrently marking. So there are barriers. You can use barriers to do that as well, to do some part of it in hotspot, for example. And the remainder at any given time, once you have gone through your marking and identified the objects that are live, hotspot brings the application threads to a safe point, and then it does the actual moving, and that's how it does its, so to speak, a garbage collection. Now, When the application threads are brought to a safe point, that's what it is called as a pause, because your application has paused for the garbage collector to do its job. And that pause is basically dependent on the copying cost, like the moving cost. So more live objects that you have to copy, that's how much time that pause is going to take, right? At least it should. There could be other issues, right? But the majority of the time that you're spending pausing should be your copying time and your moving time, which isn't in hotspot, it's copying time. So I guess that's what is a pause.
Back when the web started, people were putting up with 5 to 10 second page load times. So if you had a 500 millisecond garbage collection pause, it didn't really impact application behavior. But networks have gotten a lot faster. Applications, JavaScript, so you don't need to load your entire page. User expectations for how responsive they want application to be have really grown. And what is the impact of pauses on responsiveness of applications and on user experience?
Well, yeah. So user experience and application responsiveness can be two different things. A user may not. So your garbage collection pause of 100 milliseconds, a user may not be able to notice that if it's just ever once. So it's the frequency of the pause as well, right? If the 100 milliseconds are back to back, of course you're going to notice it. But if the 100 milliseconds are ever so often, every 1 second or so, the user may not notice it, and because network latencies could be even more, like you mentioned, could be more consuming than that. So now, how does it affect the responsiveness of the application? Like again, it's the frequency and the pause duration itself, and eventually this latencies affect the throughput. If you think about it, how often you pause and how much you pause will determine the throughput of your application. So throughput is basically garbage collection. For garbage collection, the throughput is basically the time that you spend or your application spends not garbage collecting, right? So the more frequent the collections happen, then you are spending time garbage collecting, right? So it does affect your throughput, and that's what could bring your application effectiveness down, because you're not able to process as many requests, or you're not able to handle so many federal requests or something like that. Yes, okay. And eventually down the line, what happens is it adds up. So while you are pausing for garbage collection, so many requests came in, but you were not able to handle. So now your queue, whatever queue you had, will have an impact, and then it's like a deferred, because now you have to handle more requests, and again all these things. So the queue gets impacted because of your pause.
If I have an application where I want very uniform, predictable latency without outliers, I might be looking at bringing on more servers that are going to operate at each one at a lower throughput, or maybe rotating servers on and offline so I can do the more disruptive garbage collections when the server is temporarily detached and then bring it back online.
Yeah, people do that. People, it's crazy and important that how people have learned to live with what they had. So they have learned to live with the CMS collector. They've learned to live with the serial Mark Sweep compact full GC, fail-safe GC. So that's exactly what people do, and it makes sense in many places. I know G1 GC is not there yet where predictable times are concerned, but most often than not, if you have little flexibility in your worst case response time, and then G1 GC can be tuned such that you do not encounter an evacuation failure or a promotion failure with G1 GC as you would have had with CMS. The fragmentation issue. If you tune a garbage first collector appropriately, and if you give it enough heap and you have not strict, like not 10 milliseconds pass time requirement or something. G1GC can actually be tuned in most cases to avoid that full compacting, single-threaded mark and sweep compaction. So yes, I mean, people just have to, I guess, in a way, learn more about this new collector. And one of the things that I'm doing actually is I'm giving talks about garbage first, garbage collector, because in OpenJDK 9, Java 9, one of the things is that G1 first, garbage first, garbage collector is going to be the default collector. Up until now, the parallel GC collector, the throughput collector, was the default collector, but Java 9 will bring about G1GC as a default collector. So there's a lot of education that needs to be done, and people need to try and try this G1GC collector and bring their observations to the table, talk about it in OpenJDK forums, so that there's more observation related to how to make garbage first, garbage collector better.
If I get to the point where I'm going to take a server offline because I want to avoid visible garbage collection behavior, then to me that sounds like I've almost given up. And before I would do that, I hope I could tune the JVM. What are some of the things that customers or users want the JVM to do, and how do they express that to you?
So most often than not, again, JVM and GC are kind of, when somebody comes to me, they talk about the problem areas. Most often than not, it's got to do with the tuning, like you mentioned, and at that particular point, they're not even concerned about the worst case, because they already know there's some low-hanging optimizations that can be done, and so they think that they haven't even achieved a proper scalable run, a scalable set of options where they can go ahead and talk about the absolute worst case. So simple things where, for example, references are a big thing. So turning on parallel reference processing, that helps them a lot. Sometimes just sizing the generations a little bit, or trying to find out their live data set. I mentioned that briefly. Trying to find out the live data set is a big thing. Sometimes people are not aware of compressed oops on heaps as much as 64, I guess, now with JDK 8. So if you do the alignment, if you change the alignment to 16 bytes, you can achieve compressed oops. It's not the same as with 8 bytes. It's but it's still, you're still getting compressed oops up to 64 gigs of heap. So there's some kind of education that needs, because of this. So Java is JVM is getting better, right? And every time we move to a different from 6 to 7 to 8, there are so many different things that education is the key. People need to be aware of. There's so many other optimizations within the JVM itself. There's the NUMA. People are using that now, but there was a whole education of using the NUMA-aware allocator. So things like that are just low-hanging fruits that people. I mean, not everybody that I work with need to be there. Some of them, they're very savvy and they already know what they need, and it's just a matter of looking at the application, profiling it, and figuring out what's going on, what's causing these increasing references issue, or what's causing some kind of scalability bottleneck, and sometimes profiling the heap itself, sometimes thread profiling, sometimes the application profiling are the way to go. But yes, there are lots of options that people can learn about with respect to their to the JVM.
What are some tools that performance engineers use to understand how their garbage collection is working and pinpoint areas for improvement?
One of the things that I tell all my clients is that there are two options that everybody should enable in production, and that one of them is XX print GC details, and then the other one is print GC timestamps or date stamps. With those, and then redirect your GC log, and you do the log rotation or whatever you need to. But with those enabled, I can see basically how your generation are getting filled, the allocation rate, the promotion rate. I can see those simple things, and we can talk about that just by looking at your GC log. I can look at your heap occupancy, how the occupancy, not just your heap size, how it grows, but how the old gen occupancy changes, how the young gen occupancy changes, and all these things are easily visible just by doing the print GC details and print GC date or timestamps.
Okay. So when you turn on these GC details, you get output out to a log file that it gives you a lot of information about what's going on during garbage collection, and then you could maybe parse that and feed that into some kind of statistical or analytical software and average it over time, things like that.
Well, what I don't look at averages. What I look at is all those actual GCs. So I will plot all these actual GCs. There's something called GC histo. So I'll parse this log file and provide the information that GC histo needs. And then GC histo is basically a histogram, and it provides you information. It can actually visualize these individual events, and then you can see how much time each of those events took. And then I can, if I see that, one of these collections is going past, say, 500 milliseconds, so I'm going to go investigate that further, and then that's how we start. But if I don't even have that much visibility into the GC, then I don't get the starting point. So definitely enable print GC details and print GC data timestamps, and look at the logs.
I see. So it's more like debugging, where you're looking at individual cases rather than aggregated behavior and trying to understand what happened in each individual case.
Yeah, by the time somebody comes to me, they have a problem. So we know that they are looking for a detailed analysis, and at that time, looking at averages is not going to help me at all. Maybe looking at 99. The 5 nines or whatever, yes, that will help me. Maybe looking at the worst case, of course, that's going to help me. So now that we have figured out what the worst case is, I still need to figure out what events led up to that worst case, right? So that's why I need to look at the entire set of events to identify what happened. So it's kind of a pattern. I'm looking for patterns in the log, and I'm trying to plot the same information in different ways. I look at the occupancy. So what happened here? Why did the promotion rate go up, or what happened here? So I can go back to the people and ask them, hey, I see this allocation pattern changes, and I think that because of that, there's something with the promotion rate that changed, or whatever. I can talk about these different things if I can visualize what happened to the garbage collector, so to speak, right? So
sure. And then you need to find one of the many parameters that affect garbage collection that you think will impact the cause of the issue, and try setting that to a different value.
That is correct. Yeah.
Redo the experiment.
That is correct. So very simply, when I do get a log, most often than not, they may have some options in there that are not necessary, or sometimes they're kind of tightening the flexibility that the garbage collector needs. So I start with something, or I try to get a baseline first. So by simply looking at the first log, I can say, hey, remove that option if you can, and this one, and that one, and that one, and just kind of clean up the command line option, and then ask for a baseline. Sometimes the baseline may have a little more than just the max and min heap and pause time goal. For example, in G1 GC's case, I may even have the marking threshold adjusted. But that would be the baseline. After the baseline is established, then we go ahead and try improved set of options, for that, I may ask for more. For example, there's something called print adaptive size policy, which tells me when you enable that, it tells me exactly what G1, GC, how it made up its collection set, how many regions were in each collection set, and gives me all these other details like why did this mixed collection start, and with these sets, and what's the percentage, how much each collection was able to retrieve, how much free space. Okay. So all that info. So eventually we will just keep on adding these kind of diagnostic options so I can figure out exactly what is wrong and how we can make it better.
I see. Do you combine your knowledge of how each garbage collector works and what that garbage collector is trying to do to interact with the system to drive your choice of which diagnostics are going to give you the most information? Yes. And then that will drive a hypothesis of what it is you could change to improve the performance in the way you want it to go.
Yes, that's right. And more often than not, experience matters, right? When I look at a log and when somebody else looks at the log, I can see a pattern, and I'm thinking, okay, that's something that I need to investigate, And if I show the same log to somebody else, they may or may not be able to see the pattern, or they may find something else altogether, which is awesome as well. So, it's all about it's a fun game, fun interactive game, and keeps me very interested all the time because I learn so much from it all the time as well. And now I kind of have. Every time I see a pattern, I'd say, okay, this is what it is. Let's do this, and then after that is achieved, let's try this option. So, at any given time, if I'm tuning, I'm only adding one option at a time because that way I can see, and they can, and of course they can also see the impact of that option. So that way I can explain to them first why I think that the option is important, and then second, once they see the impact, they can also validate what I was saying, and it kind of helps them understand going forward their application behavior and how the GC needs to cope up with it or whatever, right?
Right. Well, very scientific in your approach. I've also heard some developers say that server technologies that need predictable latency should not be written in a garbage collection language. And you are seeing some servers written in C and C++. They may believe that it's impossible to tune, or that just the difficulty of tuning is so great that they want something that can be more under their control. What is your view on that whole debate?
For me, it depends on the pastime goal they're trying to achieve. People that are trying to get microseconds or less than 1 millisecond for sure, but like less than. So in that range, yes, everything, you have specialized like FPGAs and stuff like that too. People are doing that, co-locating, like when you're doing the trading, you want to co-locate as close, not have the network cable run all the way, where speed of light matters. In those cases, yes, I mean, Java is not a competition. Right, because what is Java? It's abstraction, right? So when they want to get to a particular field directly, and they want to make changes directly, so allocation, they want to be in charge of everything that they're allocating, and so yeah, I mean, it does make sense in that very, very low latency arena, When we talk about servers, I don't think most of the servers need that much of specific low latency requirement. They don't have that kind of requirement because network is the most dominating latency factor, right? So if somebody tells me that I have servers, one in this region and one in the other region, and I'm trying to optimize garbage collector, and then I would like to have data from both of them and try to figure out if garbage collector is in fact a problem. Sometimes people blame garbage collector for everything, right? But then I try to look at their application logs. I try to look at the garbage collector log. I try to put it all together and try to tell them that, see, your garbage collector was at any given time not over 500 milliseconds, didn't experience over 500 milliseconds pause. But your application is having this kind of issue. So maybe we should investigate something else, right? Safe points are another reason, it doesn't have to be safe points like stop the world, doesn't have to be just garbage collector. There are other reasons why that could have happened. So we go and investigate something else as well. Garbage collector may not always be the issue.
I've also seen some talks like Martin Thompson in the LMAC system where they adopt programming techniques to stay off the heap, like allocating big chunks of memory and creatively reusing them in ways that were probably not thought of by the developers of the Java language. Do you think some kind of mix of specialized programming techniques and garbage collection is a pragmatic solution to the needs of very high performance applications?
Yes, Martin Thompson, Peter Lowry, and a couple other people that I know of are totally doing exactly what you said, and it makes sense because again, the realm that they are in, the goal that they're trying to achieve, they're trying to reduce allocations. They're trying to, again, the whole thing about garbage collector is not just the collection itself, it's also the allocation. Sometimes people, and at allocation and the expense those allocations come with, So I think what they're doing makes perfect sense for the field that they're dealing with. And yes, so bottom line is yes, it does make sense.
I'm aware that in a upcoming version of Java, there will be support for staying off the heap for programmers that want to avoid garbage collection. Could you explain how that's going to work?
So in Java 10, actually Java 1 this year, the keynote, one of the keynote speakers, Brian, mentioned about Project Panama. And what it does is that it aims at giving JVM direct access to the native data, like data in the native heap, and also code. For example, if you had C functions and stuff like that. So there's a tool, I think it's called JExtract, and the way that works is that it extracts the metadata, for example, the header files and stuff like that, and it generates its own. So it does it for you, basically. It generates these Java interfaces. So that way, it gives you this kind of way to work with your code and data. So it's pretty cool the way it works. And Brian actually walked us through with an example and how he could call, like there was a time library and also struct, which is like really a pain point, right, of Java. So Brian showed us an example how they could do that. So then eventually end up just calling the getters and setters to the fields directly because JExtract does everything else for you. So it's pretty cool. Yeah, it's called Project Panama.
Great. And as a final question, where do you see Java garbage collection going in the future? Would you say it's pretty much a solved problem and a mature technology, or are there going to be more developments and improvements in this area?
Oh yeah, there's going to be a lot more improvements to this area. I think today, as far as hotspot is concerned, we are at a good starting point. It sounds ridiculous coming from a person who has worked with garbage collectors for more than a decade, saying that today is a good starting point. But what I mean by that is that we have learned a lot. We have learned from the throughput collector. We have learned from the low latency collector. We have learned, and that's what gave us G1, GC. After all the learning and the education about scalability bottlenecks and about incremental compaction, how to do it right, we have learned about that. But we haven't yet mastered deterministic collection yet. We haven't yet mastered without having a super expense on throughput, right? So we haven't mastered that. We haven't mastered larger heaps. With G1, yes, that's a starting point. But what about G1 for throughput? What about G1 for low latency? So those are the next steps. So I envision a future where the regionalized heap framework is going to be the base framework for garbage collection. And I also see specialized effort towards gearing garbage collectors towards low latency, predictable latency, and deterministic latency, which means that you could move towards, no stop the world pauses or something like that. So there's already work done, like Azul has worked with this, and they deal with very large heap sizes and no pause, right? So there's work done, and I see OpenJDK hotspot moving to that realm. I also see throughput collection moving to the regionalized heap framework. It's so much easier when your adaptiveness is just based on adding or subtracting a region, right? Instead of having pre-allocated area where you could expand to in the future in a contiguous heap manner. So there's lots of issues with the existing GC frameworks. I think G1 GC's framework is going to be the new norm. And of course, IBM has their balanced heap, I think. There's another Shenandoah, which is also a regionalized heap. It's an OpenJDK proposal, I think. And so I see that as the future.
Great. For our listeners who'd like to learn more about your work or follow you, where should they go?
Well, I write articles for InfoQ, so it's infoq.com, and then just my name, Monica Beckwith. Just look me up. You can follow me on Twitter. It's monbeck_Beck, MON_Beck. And that way they can reach out to me on Twitter, and then I can help them with their needs. So, yeah.
Monica Beckwith, thank you very much for speaking to Software Engineering Radio.
Yeah, thank you.
For our listeners, we would love to get feedback from you. You can email us at team@se-radio.net. Follow us on Twitter at SE-Radio. Contact us at our group on Google+, LinkedIn, or Facebook, or go to iTunes and write a review for the show. For Software Engineering Radio, this has been Robert Blumen. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE-Radio, or search for the Software Engineering Radio group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.